Hi dear friends. Dear friends, in the last part of the video, we discussed a colligative property known as depression of freezing point in the chemical thermodynamics. Dear friends, today in this part, we will talk about osmotic pressure. How this osmotic pressure is depends upon the concentration of solute in the solution, and it is a colligative property that we will discuss today. Dear friends, before discussing osmotic pressure, we should know what is osmosis. Let us see. Here you can see there are two compartments. One is the compartment containing solution of NaCl and another compartment is containing a pure water. These two compartments are separated by means of a semi-permeable membrane. So this is the semi-permeable membrane. What happens? It is observed that the solvent molecules from this pure water, means the solvent compartment, spontaneously move into move into a solution compartment through this semi-permeable membrane. So this this spontaneous transfer of or flow of solvent molecule from solvent to solution through the semi-permeable membrane is known as osmosis, or it is also defined as the spontaneous flow of solvent from dilute solution to the concentrated solution is also known as the osmosis. So this is a very important. There is a transfer, there is a flow of solvent molecules from pure solvent to the solution or from dilute solution to concentrated solution through the semi-permeable membrane. So dear friends, whenever we want to study about the osmotic pressure, so to stop this osmosis, means to stop the flow of solvent from solvent to solution or from dilute solution to the concentrated solution, the whatever external pressure or the pressure is exerted or pressure to be exerted, that pressure is known as osmotic pressure. It's very simple to discuss about this osmotic pressure, and already we have discussed about osmosis. So this osmotic pressure can be defined as the minimum pressure which is exerted or that is to be exerted on the solution to stop the flow of osmosis from solvent to solution when separated by semi-permeable membrane. So this pressure is known as osmotic pressure. In order to derive the equation for osmotic pressure, there are two laws given by means of Ventov. Actually, he has observed that the osmotic pressure results from, or it is due to the kinetic motion of solid particles on the walls of the semi-permeable membrane, and based upon the same he has given the two laws. The first law is known as Ventov's law, and according to the Ventov-Boyle's law, the osmotic pressure is inversely proportional to the volume at constant pressure, and for that purpose definitely the equation is pi is inversely proportional to volume, and therefore pi v is equal to constant. This pi is known as the osmotic pressure, v is the volume of the solution. Another law is known as the Ventov-Charles law, and according to a Ventov-Charles law, the osmotic pressure is directly proportional to absolute temperature at constant volume. Therefore, pi is directly proportional to absolute temperature T. Therefore, pi upon T is equal to constant. So, based upon the same, if we will try to combine these two equations, both Ventov-Boyle's law and Ventov-Charles law, we will get the equation pi v upon T. Pi v upon T is equal to constant, and that constant is nothing but the R. So therefore pi v is equal to R into T for 1 mole of the substance, and for n number of moles, definitely the equation is modified as pi v is equal to nRT. So definitely, dear friends, We can also derive the thermodynamic derivation for Vent of equation based upon the chemical kinetics of solvent in pure solvent and the solution. The chemical potential of the solvent in the solution is mu of solvent plus osmotic pressure, while the chemical potential of solvent in the pure solvent is only because the solvent. So this is mu of solvent. Pure solvent is at atmospheric pressure P. P is the atmospheric pressure. So pure solvent has only atmospheric pressure, and while the solution is having a pressure P plus pi, that is atmospheric pressure plus osmotic pressure, on account of additional pressure due to osmotic pressure. Therefore, the chemical potential of solvent at pressure P is given by mu 0 of P, while the chemical potential of the solvent in the solution is lowered by the solute, and it is raised due to the greater pressure P plus pi acting on the solution. And therefore the chemical or the potential equation for the potential is given by means of pen. It is indicated mu of x P plus pi, and at equilibrium mu 0 of P is equal to mu 0 of x and P plus pi. P plus pi, this is pressure, and x is the mole fraction. X is the mole fraction of the solvent. So therefore this mu of x P plus pi can be modified as x mu 0 of standard potential P plus pi plus RT ln of x. X is the mole fraction of the solvent. Therefore mu 0 of P plus pi is equal to mu 0 of P plus VdP. From this equation, from these two equation, that is from these two equation, this definitely this side equal this mu 0 of P, this also pressure, mu 0 of pressure. So RT ln of x will be equal to what? RT ln of x will be equal to V into dP. V is the molar volume, P is the pressure, dP is the extra pressure on solution, and this extra pressure is known as the osmotic pressure. Therefore this equation can be modified as pi into V prime plus is equal to RT ln of x. V prime is the molar volume of solvent, x is the mole fraction of solvent. So this mole fraction of solvent x is equal to 1 minus x prime. X prime is the mole fraction of solute, and if it is put in this equation, we are getting ln of 1 minus x prime, that is simplified. Finally we are getting pi V prime is equal to RT into x. So this is very simple regarding with the regarding with this equation. So mole fraction of solute x prime is given by means of this equation, just like the n1 divided by n1 plus n2, n1 plus n2, x prime is equal to n, that is number of moles of solute divided by the sum of number of moles of the solute and the solvent. But as compared to solvent is very greater, means number of moles of the solute is negligible. That's why this can be considered as negligible, 0. So definitely x prime is equal to n of number of moles of the solute divided by number of moles of solvent. Finally we are getting this equation pi V prime is equal to, that is number of moles of solute divided by number of moles of solvent, and that can be modified as pi V prime is equal to n RT. V into n, this is the total volume, n RT, and this equation is similar to ideal gas equation, P is equal to n RT. So this can be also used to determine the molecular weight by considering the number of mole in the terms of W upon m. So this is very simple. Again, it is also observed that sometimes if the electrolytic solution is prepared, then the observed colligative property is going to be different than the expected colligative property, and this is because of the dissociation. So electrolytes undergo dissociation that increase the number of particles in the solution, definitely that affect the colligative property. And in this case, if we will prepare the solution of sodium chloride, then it produces sodium plus plus Cl minus, and the osmotic pressure in this case, as it is the colligative property, it means it is depends upon the number of particles in the solution. Therefore osmotic pressure of electrolytes is more as number of particles increases than the expected. Therefore observed molecular weight is going to be smaller than the actual or the expected molecular weight. So this is the equation. Similarly, whenever there are some substances which undergoes association like collides, so in case of an electrolyte, the the molecular weight of the electrolyte is observed less than the ideal value. But if the substance undergoes association, the number of particles decreases. Therefore, the observed osmotic pressure is found to be less than the ideal value, and therefore molecular weight, observed molecular weight, is going to be greater than the actual molecular weight. Therefore, molecular weight of colloids polymer is found to be more, always more than the ideal value, and the ratio of this observed colligative property to the expected or the ideal colligative property is known as the Vent-Off factor. Is known as the Vent-Off factor. Therefore, for electrolytes, the Vent-Off factor I is greater than 1. Is greater than 1. Therefore, observed osmotic pressure is going to be greater than the real or the ideal value. That's why observed molecular weight is going to be smaller than the actual molecular weight. Similarly, that can be applicable for the colloids also. That for colloids like starch, this Vent-Off factor is less than 1. Therefore, observed osmotic pressure is going to be smaller than the real or the actual osmotic pressure, and therefore observed molecular weight is lower, is greater than the real molecular weight. So this is important case. But for the ideal solution, this Vent-Off factor means the ratio of observed to the actual collective property is going to be 1. Therefore, Vent-Off factor is 1. Therefore, observed osmotic pressure is going to be equal to the expected value of osmotic pressure. So this is very simple regarding with this. For the electrolytes, we can show the dissociation, and as the number of particles increases, therefore Vent-Off factor is equal to 1 minus alpha plus n alpha divided by n. After modifying, we are getting I is equal to 1 plus alpha into bracket n minus 1. Therefore, I is always greater than 1 for the electrolytic solution, while for this colloids, that I is equal to 1 minus alpha into 1 minus 1 upon n. So this I is going to be smaller than the 1 for the substances which undergoes association. So this always going to be I, Vent-Off factor is always going to be smaller than the 1. So this osmotic pressure can be calculated, and the whatever method is employed for this determination of osmotic pressure is known as the Berkeley and Heartless method. In this case, what are the things? Actually, this method is based upon the principle in which the external pressure is applied on the solution just enough to prevent the osmosis, and this apparatus used is known as the osmometer, and this osmometer consists of the porous porcelain tube with a copper ferrocyanide membrane deposited on its wall, which is thin then enclosed in a metallic jacket. One end of the tube is fitted with the reservoir of pure solvent like water and capillary tube at the other end. The jacket is filled with the solution, those whose osmotic pressure is to be determined. Let us see how is the. So here you can observe this jacket of this tube is filled with the solution whose osmotic pressure is to be determined, while this tube in which this part is filled with the pure solvent like water. What happens? These two are separated by means of a semi-permeable membrane or the porous membrane or semi-permeable membrane. This is the porous tube with semi-permeable membrane. What happens? Due to the natural osmosis, this water molecule will move. This water molecule will move from solvent to solution, means they will flow towards the outer jacket, and that's why the level in this capillary will start to level in this tube, in the side tube, is try to increase, and hence this level increases. But if the enough pressure should be applied, should be applied with the help of this piston, at which the level of liquid in this capillary remains constant, remains same, and that pressure which is applied, that enough pressure which is applied at which the level of the liquid in this capillary tube remains constant, that pressure or this pressure is known as the osmotic pressure. So this pressure can be read by means of a pressure gauge which is present here. So this is a way by which we can measure the osmotic pressure, we can determine the osmotic pressure. So dear friends, today in this part of the video we have completed what is osmosis, what is osmotic pressure, and how we can determine the colligative property for the electrolytic solution as well as for the substances which undergoes association. And also we discussed about how we can determine the osmotic pressure experimentally by Berkeley and the Heartless method. So this is a simple way by which we can study about the osmotic pressure. So in this way we have completed this chemical thermodynamic. Thank you very much.